So good evening, ladies and gentlemen. I'm Engineer Prasanna Narangoda, the Chairman of Building Services Engineering Sectional Committee of ISL. So you all are warmly welcome to the public lecture today on a very important topic and very timely important and very emerging topic is building services application with infrared thermal imaging. So I'm sure that all of you will be getting benefited out of the presentation and the information sharing by the presenter speaker today. So our speaker is Engineer Shami Mudunkotua. He's a very competent engineer and also really passionate about this area. I'm sure that he will be sharing his past experience and knowledge with you about the infrared thermal imaging. So Engineer Mudunkotua, thank you very much for accepting our invitation and presenting here today to deliver this public lecture. So I cordially invite Engineer Kaushal Pathirana to do the introduction about our speaker. Very quick introduction. So he will, Engineer Kaushal Pathirana, please take over. So before that, I'll give a small reminder that all of your mic should be kept mute mode till the presentation is end. And if you have any questions, please forward your questions into the chat box. Moderator will take over all the questions after the presentation with the speaker or the presenter. So Engineer Kaushal Pathirana, please take over to do the introduction. Thank you very much.
Thank you very much, Engineer Narangoda. Good evening, ladies and gentlemen. I'm Kaushal Pathirana from Building Service Engineering Sectional Committee. I warmly welcome you all to the third webinar organized by the Building Service Engineering Sectional Committee for the session 2020-21. Today's webinar will be very exciting and will be beneficial to many engineering fields. The topic is building service applications with infrared thermal imaging. Infrared thermal imaging, in short words, IRT, is a fairly old but vastly developing technique and globally using for endless amount of applications, especially in building service engineering fields such as electrical, mechanical, MVAC in both industrial and domestic applications. Today's objectives of the webinar is to provide an introduction to this technology while debunking the myths around it. Hopefully, we can have a glimpse of different applications related to many professions. Thank you all for joining with us, and let me introduce our speaker today. Engineer Shami Mudunkotua was graduated from Department of Electrical Engineering, University of Moratuwa, and a chartered electrical engineer, currently working for Ceylon Electricity Board. With a master's degree in electrical engineering, he is currently serving as a contributing member in the 4-member steering committee appointed by the National Centre for Non-Destructive Testing Atomic Energy Board in Sri Lanka to establish the first ever training course on infrared thermography in the country. Engineer Shami is well experienced and carries great exposure in the IRT field and has a special interest in infrared thermography techniques for predictive maintenance. It's our pleasure to introduce him as the only level 3 certified infrared thermographer in Sri Lanka. Having Tyson closely collaborated with many foreign professions on the subject, Engineer Shami has a broad vision of unlocking and expanding the industry of IRT applications in Sri Lanka to gain the maximum benefit to the national industries with the proper use of IRT. Well, ladies and gentlemen, without any further ado, please join with me to welcome our speaker tonight, Engineer Shami Mudunkotua. We are delighted to have you in this forum. And one more thing, I would like to remind you that there will be a Q&A session at the end of the presentation, and you can post your questions to the moderator by selecting the moderator in the chat box during the presentation. And we will direct your questions to the speaker at the end of the presentation. Now let's move on to the presentation. Over to you, Engineer Shami. Thank you.
Engineer Shami, your mic is off.
Okay, let me start over. I'm really sorry about that. Thank you so much, IESL and the Building Services Engineering Sectional Committee to having me today and giving me this opportunity to present this the little knowledge I have on the subject. And when I met with the officials yesterday, Mr. Narangon and his team, I clearly shared my idea about this presentation, and they very warmly welcome my ideas. And I'm really thankful for having me here today. And since we are having a long presentation ahead of us, let me move on to the presentation. Needless to say that this field is heavily underutilized in Sri Lanka. We see a lot of foreign footprint on the local market to provide these services, which in my opinion is not really necessary. At the end of this presentation, I'm sure you will be convinced and agree with my view on this. So my goal here today is to give you a little glimpse of the uh, literally endless number of applications we have with thermography, and how to get the maximum amount of your device you have right now. So I'll be moving on with the presentation. So just a little self-introduction about myself. Um, so I have been engaged with this since 2011 when I was working for Leakages, call handling maintenance. I had a wonderful experience there, and recently I have been invited to the Atomic Energy Board, the National Center for Non-Destructive Testing, to establish the first ever training course, and I hope that we'll be able to launch it very soon. And hopefully the officials from the board are also present here today. So yeah, my contents for today. First, I'll be touching on the basics of the thermography. Mind you, this is a there is a huge theoretical background to this. When it comes to level 1, 2, and 3 training, special level 1 and 2, the training courses are around 30 hours long. So I'm trying to kind of squeeze in the very basics within this 1.5 hour presentation, and please bear with me if you feel a little uncomfortable and feel a little hiccups in the flow of the presentation, as I'm trying to squeeze in as much details as possible. But I'm really looking forward to the final Q&A session where this discussion would be really interesting. That is my #1 priority today. So, so after the basics, I'll be touching on the applications a little bit, on what I have seen on the field, and I have lots of images from the friends around the world. So we have a community of friends representing around 30 countries around the world, level 2 and 3 thermographers. We have a WhatsApp community where we share each other's ideas, we share images, we share experiences, and we discuss about theories, we discuss about research on how this field is, where and how this field is progressing. And after that, I'll be finally touching on the real field experiences and the training and bit of certification. And as clients, what you should be looking at the thermographers when you are trying to obtain their services. All right, the basics, a bit of thermal basics for you. There are 3 methods of heat transfer. When you have a heat source, you can either, the heat can transfer by conduction through a solid, and convection through a fluid, and radiation through the space. So these 3 possibilities, what we feel if we have a, for example, if I'm having a fireplace in my room right now, so the sensation I'm feeling coming from the heat source, we measure it as a temperature. That's what we feel. That's what we feel, right? That's how we measure the physical quantity of heat. We measure is the temperature. That's a measurement of the amount of heat we feel. And this science has a lot to do with how materials react to heat. When certain material gets exposed to a heat source, what kind of phenomena takes place on the surface and inside the material. But unfortunately for infrared thermal imaging, we don't know what's going on inside the material, but on the surface, we will have a better idea. But again, when you know what's going on the surface, if we know what the material is, we can very well and very correlately relate to what's happening inside the material. So there are parameters like specific heat capacity, conduction coefficients and convective coefficients, cooling, inherent material builds, metallurgy, and of course, radiative coefficients and the atmospheric conditions as well. So taking all those basics into mind, let's move on to the physics of the radiation. So out of the 3 methods we have, here we are only interested in the radiative heat transfer, the radiation. That's the method of our interest. So radiation is, basically speaking, it's very simply speaking, it's energy traveling through space. Electromagnetic, and we call them photons. So it can conduct through any medium. Of course, the medium traveling can have an effect on the attenuation of the electromagnetic waves, things like humidity and atmospheric temperatures. If there are any other foreign gases or any other solids exist on the way, they will have an effect on these photons traveling through space. So the very base of these studies, the radiative heat physics, it was found by 2 gentlemen called Stefan, Ludwig Boltzmann, and Joseph Stefan in late 800s. They derived this equation that says the amount of radiative heat transfer from a body on a certain temperature. So you can see Q is the radiant heat from a certain body. That particular heat emitted by the body is equivalent to the product of the emissivity of the body. Emissivity we will touch later because that's a very, very important aspect in our discussion today. And Stefan Boltzmann constant is a universal constant, as you all know from your high school physics. And the absolute temperature, of course, from Kelvin. So this emissivity is a property, a material property we discuss when it comes to infrared thermal imaging, and undoubtedly it's the most important parameter you need to look at if you are trying to measure, take an infrared thermal imaging reading. So, thermal physics continued. This is the electromagnetic spectrum. Your photons, the infrared photons travel from 0.75 microns to 1000 microns in wavelength. For our studies today, for the devices we are talking about today, and the most of the devices we found in industry operate in the spectrum from 2 microns to 50. That's the band, the sub-band of the infrared that contains, again, broken into 3 sub-bands. The short wave from 1.2 to 3, and 3 to 8, you have the medium wave, and 8 to 15, you have the long wave. So today, for our discussion, we will be looking at the long wave infrared images from 8 to 15. Sometimes it gets 7.5 to 14, and likewise. So this is the these 3 gentlemen laid the very strong basement for the devices we carry in our hands today, right? Sir William Herschel first discovered the infrared rays in 1800, and following his studies, these 2 gentlemen, Joseph Stefan and Ludwig Boltzmann, discovered the famous Stefan Boltzmann equation for radiative heat transfer. And they developed this equation for things like, they spoke about 3 bodies. That's a black body. Black body is an ideal material that does not exist in the real world, that the emissivity equals to 1, which means that all the heat it absorbs, they emit, and the equilibrium is very well achieved for all spectrum. The full spectrum of infrared, the emissivity is the same. And we also discuss about gray bodies and real bodies, which are far from the ideal case, which is a black body. They don't have perfect emissivity. They always have emissivity less than 1. If we are lucky on the site, we will have emissivity of greater than 0.9, which we are talking about the cable insulations, the PVCs, the XLPEs, and the insulation tape, 3M insulation tape we usually speak, they have emissivity of about 0.93, and sometimes it's 0.98. But the thing about the emissivity is never a static parameter. It changes with temperature itself. So if you have seen these emissivity tables, they always define the values for a certain temperature. Usually it's for the room temperature at around 25 Celsius degrees, and with the band, with the subband, whether it's short wave, mid wave, or long wave, again it changes. So as we can see, the emissivity itself is a very dynamic parameter. It's never a static parameter. You should keep that in mind. Going on to some concepts. So why we need contact and non-contact measurement? So as you know, the infrared thermal imaging is a non-contact technology. We don't have to touch the surface to get the measurement out of it, right? But on the contrary, when it comes to other devices like resistive thermal RTDs, the thermocouples and thermistors and other instruments, they always have to touch the surface, right? So they are contact forms of measurement. But the infrared thermal imaging is the only way we can get a non-contact measurements of from out of a material. So we need to first understand what are the advantages and the disadvantages of both of these technologies. With that understanding, we can see where we can benefit from the thermal imaging and where we can benefit from the contact measurements, right? So non-contact measurements like thermal imaging, it's really fast. We are talking about 1/9 frames per second, right? You're talking about a speed of 9 frames per second measurements, which means if the temperature is varying, uh, we can take 9 separate measurements within 1 second. In which with contact measurements, that's not possible because contact measurements are delayed. For example, if we are trying to measure our body temperature, we at least need to keep the thermometer under our arms or in our mouth for about, say, 1 minute to achieve the equilibrium, so we can have a better reading. So with thermal imaging, that's not required. But however, if you are trying to measure temperature um, um, from a distance, there can be other limitations like atmospheric compensation and things like um, interference from the environment can affect your reading. So the accuracy can be less in thermal imaging and other non-contact forms, but in contact measurements, those limitations are not there. So non-contact measurements are fast, mostly safe, and can be done remotely, but expensive and less accurate. On the other hand, contact measurements are highly accurate, but they are really slower than non-contact measurements, and mostly unsafe. You cannot touch most of the surface on the industrial environment you are trying to measure, and you cannot do it remotely. You have to be on site. You need to have a probe on site itself. But it's inexpensive. It's cheap, right? We'll discuss how cheap they are and how expensive thermal images and devices can be. But again, with recent technological developments, there have been groundbreaking price reductions in these devices. I will come to that later. So for some of the professionals who are thinking um, infrared thermal imaging is a simple point and shoot technology, I'm sorry I have to disagree with you, because when you buy a camera, a DSLR, say, you can become a photographer instantly, right? You can start shooting instantly. You buy the camera now, you start shooting now. You can go on a safari trip on the day after and take some cutting edge photographs using it, but not with thermal imaging. No, sir. This is not a simple point and shoot technology if you don't understand the physics and how these devices work and what are the limitations are. If you don't have the training and sometimes the certification, you can make life-threatening well,
Engineer Shami.
Yeah, can you guys hear me?
Engineer Shami, the line signal, I think signal little weak and getting disconnected. The sound is getting disconnected. Okay, can you check again now?
Yep, I think you guys can hear me now, right?
Now it's okay, yeah, clear. Okay.
All right.
Okay, thank you.
Yeah, so I was talking about how these devices can fool us, right? If you are not qualified enough to use them. So, so I'll be touching a little bit about the relevance about the building service applications today, and all right. So here, first I'll be touching the electrical applications. You have a lot of electrical appliances in your buildings. Maybe your high-rise building. It can be your factory, can be your warehouse, can be your house. So there are a lot of electrical appliances. There is a distribution system. There are critical assets at work. So how can we monitor and do predictive maintenance on those applications? And then I'll be touching about moving up equipment like lifts, escalators, pumps, chillers, gearboxes, HVAC systems, central cooling and heating systems. Heating, of course, Sri Lanka doesn't have any centralized heating systems. If we have, there must be really few. But overseas, when where the winter and the summer is hitting really hard, the centralized cooling and heating systems play a really vital role. I'll show some photographs. I've got some from my friends from US and Europe, how they monitor those assets. And the building services engineers, they hate leaks, right? You see a water leak, you see a leak, water droplets from a leak. That's a huge headache for the building services. So I'll show you some photos where you don't have to, break the concrete. You don't have to break the earth to find a leak. If you know how to use this technology with the right terms and parameters, and you can check your buildings, you can see your structural members with it if you want. There are many applications. So moving on with some images right now, right? For electrical, this is a transformer. This is a typical low voltage transformer. So here you can see there is a hot connection. The temperature is about 130 degrees, which is really dangerous. These values you need to compare with your cable insulations, right? So the cable insulations, the PVC and cross-linked polyethylenes are designed to withstand up to maximum of a 90 degrees C, where you have, here you have almost 130 and around 82 degrees on the middle one, and the last one is also 60 degrees. So you can see the burn marks here if you look closely. This is potentially really dangerous, right? So that is one of the application. If you see a high resistive connection, this is the most common applications that most of the engineers know. When you see something hot, you know it's a loose connection, but mostly high resistive as well, but we don't know whether it's loose or maybe it may be annealed to this terminal. It may be due to the high temperature and the thermal cycling. The terminal itself and the lug itself can be stuck together. So if you think about it as a loose connection and you ask your technician to tighten it, there is a very good chance that you will be making things worse than it was, right? If it is a loose connection, yeah, it will be okay, but we don't know for sure. To make sure, the best corrective action would be to remove the terminal and inspect. It could be the lug, or it could be the terminal, or it could be the bolt, or it could be the connection bolt as well. So remove it and inspect it, and then reinstall it. And then what you need to do is you take another image. You let it cool down. You get it to the maximum load. The National Fire Protection Agency 70 Bravo standard says that your installations should at least be 40% loaded, right? But we say that it should be 100% loaded, so that you get the maximum anomaly possible. So you know what's the baddest. From there you can work, right? Yeah. All right. This is another classic image. You can see here. We can see these three terminals are of three colors, right? This one is really red, and this one is red, but as not red as the early one. So this is really, I mean, cold, the really cold one. So you see a classic load imbalance situation here, right? So what you do is you propose the client that you need to carry out a load balancing survey, what we call, and you need to balance out the loads, right? So this is not necessarily a terminal problem. This is a load-related problem that can be more problematic when resolving. It's not that simple that you remove the terminal and reinstall it. You need to do some investigation. You need to measure the currents, how large the currents are, and you need to see why the currents are low on one leg and higher on the other leg. So you need to transfer some loads here and there, and you need to follow up again. You need to follow up with the image and make sure that it's properly loaded and balanced. Or one fine morning when you come to the office, you can see these darkened cables right here, right? We don't know, we are doing the survey on a given particular time. That's a snapshot, right? That's not a survey. The real deal happens throughout the day, right? You have fluctuating loads, you have varying processes. You'll be cycling these bad connections throughout. So you need to pay attention to those. So these are some classic images we have captured. So here you had so keep in mind there are many components in a power distribution system. There are breakers on either side of the breaker. Here it's a cable, and on the upside it's a bus. So there is a subject called evaluating your connection. So in the NEDA, we call it the National Electric Testing Association standards. They state that the maximum temperatures that you need to have under similar loads. So if your breaker is under similar load, so in this phase you have a similar load, right? So if you have a hotspot here and here, there are ways to evaluate that connection, whether it's too hot or not. So that's how we know whether it's too hot, how hot is too hot, right? So you need to bear in mind that you are comparing two different components here. So in this picture, the second one, we have a typical overload situation here. So it can be a loose connection right here, or can be a throughout overload situation. But from the looks of it, it's a connection problem. So here we can see there's another overload problem. So here in this MCB, we can see a hot contacts inside. So you can see this image here. And the lower one right here, so right here is a really nasty case. I remember this case. This was around 150 degrees here. So this is what I was talking about. So you keep on adding loads to your distribution systems without a proper knowledge and analysis. You keep on adding those loads in an ad hoc manner, and you keep on stressing your distribution system beyond the limit. And this is the disaster waiting to happen. This is exactly why you need to have a better idea of your distribution system. So here you can say, if you pay close attention here, you have a bad connection because you see a red hotspot right there, and there are some tiny details you can miss. So make sure your image thermographer must be skillful enough to identify those. And the attention to detail should be really critical. It's crazy. You miss one thing, and that could cause a fire for you, right? So the attention to details is really important. You take things slow, and you get the time out of it, and you check your time and your service. That's one thing I learned. So moving on with some more interesting images. Here you have a selector switch. So here it's an obvious connection problem. So here you have the good old ceramic, connectors. You can see the hotspot right there. It's very clear. And yeah, this is an interesting image right here. You can see from the side, these are the two contactors. You can see from the side that these contactors, internally they have many components. They have their electromagnetic coils, they have their contacts, right? So based on the thermal signature, your thermographer should be able to identify what the problem is. Is it the coil or the bad contacts? Accordingly, he must recommend suitable action. Can you guys hear me?
Of course we do.
Yes.
All right. Okay. All right, the last image. This is really visually, it's clear. You can see the copper oxide right here, and thermally what we see, right? So these situations was the ones I was talking about. You don't know whether this is a loose connection or a tight connection. To make sure, you have to remove this. You have to take this out, and you need to clean it. You need to clean the terminal, maybe cut out a little bit, and you need to clean the contactor terminal as well. You need to clean both ends and put it back, and do the follow-up survey, of course. So these are some electrical applications, some images I have captured during service. And oh yeah, this is my favorite. These capacitors, every time we see them, these capacitors, they are overheated. So I have been looking into this in detail and found that there are some inherent attributes, the design of these capacitors. So mostly the clients, they don't maintain these capacitors. There is a limit to the ambient temperature. So you can see some cobwebs right here, right? So that tells the amount of maintenance that goes into the capacitor bank maintenance. Capacitors are kind of a delicate devices, right? They don't tolerate harsh environments. When the manufacturer says it's 40 degrees ambient, you need to think that it's 30, right? You need to keep them air conditioned. You need to pay close attention. You know, if not, these hot connections, these hotspots can get, I have seen these hotspots get around 150 degrees really easy, right? Easily increased. You need to maintain these capacitor banks and you need to do the regular maintenance. You need to, during a shutdown, you need to measure the capacitance value through the terminals and make sure that the capacitance are of good shape. And there are internal design problems of these capacitors as well, because these capacitors, they, during the operation, the dielectric inside it, which is a composite material like polypropylene and refined hydrocarbons, they emit certain gases inside, which makes the capacitor expand itself. So usually you can see these, in this area, you can see a collar type of thing. So those are provided to facilitate this expansion. But what happens is that these designers, they don't know how long, for how long they will get expanded. So sometimes the internal connections to these terminals, they get broken, or they get, let's say, high resistive during the expansion. So this expansion can cause a high resistive connection, and when it comes to high resistive connections, the copper loss is really high, and the heat is shown somewhere around here on this area. So that is also, and you can see in this picture, this area has the most heat, right? So there are phenomena like that. This is a research we do these days with some of the manufacturers, and the capacitors are really interesting. And like I said, your capacitors, like each and every component in your system, undergo thermal cycling. They get current fluctuations, they get ambient temperature fluctuations, and they have to tolerate all kinds of abuse. So generally speaking, your thermal imaging survey must cover the capacitors, and you need to do the preventive maintenance of the capacitors anyway to minimize these effects. Yeah, this is another classic example. Please excuse me for the focus of these images, but the thermal details are intact. So you can see here, there is a bad contact case going on. Here, it's really hot. So the recommendation obviously should be to replace this contactor, or at least inspect the contacts, right? Contactors can be really interesting to check, right? I have some images that I have seen from the dissected contactors, how bad the contact wear can be if the number of switching cycles are high on a given day. So you need to watch out for that, right? Oh yeah, this is another classic case, which many of you MEP engineers are aware of. So if you have a three-phase connection going into a panel, so in this area right here, you have the maximum magnetic field, right? Because each of these conductors have their own magnetic field, right? So in the middle right here, they get add up. The effective field is add up, and that gives birth to eddy currents in this area. So there is a current going and a stray current on your plate.
Excuse
and,
me.
Yep.
The slides are not advancing, it seems, or the
Okay,
pointer
let
is
me,
not.
yeah. thanks for letting me know. I'll stop the share and reshare the slides. Could you please let me know from which point did I?
It's the
The capacitor bank. Yes.
All right. Let me unshare and reshare. Can you see now?
Not yet.
Not yet, yeah.
It's coming. It's coming. Yeah. Engineer Shami, shall we try to share again? I think the signal is little big. Yes, now okay.
Okay, all right. So did you guys see this? Did you guys get my explanation for this slide?
No, we couldn't see this earlier.
All right, okay. I'll continue from here then. All right. What I was trying to say is that here we have a obvious faulty contactor. Please excuse for this poor focus. So here in this contactor, you can see there is a obvious thermal signature right here. So this is a bad contact case. So this is exactly where the contacts of the contactor is situated. So you need to know, you should see that there is an obviously internal problem. All right. Here it's we call this the inductive heating, which is of course unintended. So what happens is when you have a three-phase connection, all three phases together, when they enter a certain panel, they each other have these individual electromagnetic fields, right? So what happens is these four electromagnetic fields meet each other right in the middle. So the field strength is high enough for this plate to generate eddy currents, right? So what happens is you have a stray current going on this plate, and from the copper loss I squared R is increasing now. So I have seen cases where this particular heat generated from the eddy currents from the inductive heating wear off the paint, and it gets really hot. It can get hot up to beyond 100 degrees easily given the high currents. So this image, like I told, this was shared by my man James from Thermospec Australia. So we, like I said, we share a lot of images with each other, and they use their images in their webinars, and I share mine with them, and with their consent, I share these images in my webinars. So if you want to use these images, please contact me, because I need to get their consent for you. So we have seen enough. right? We have seen enough electrical components. I think it's clear that all the components need to be checked. Breakers, current transformers, terminal bus, contactors. Bus bar systems, they can be really complex because you have a lot of connecting bolts. And remember what I told about the emissivity, right? So these bare copper bars you have in the bus trunking systems and bare bus bar systems distribution, their emissivity is really low. Using the thermal imaging, you cannot capture the true photons coming from the bus bar systems that which makes the job of the thermographer really difficult. What I suggest is that to have the what we call the bus bar sleeve, right? We have the bus bar sleeves, the matte finished bus bar sleeves, at least on the bus bar joints, so that someday when the thermographer arrives, he can get a better idea of your bus bar system. Same with all other components when it comes to bare metals. Bare metals are really low in emissivity. You need to actually make sure that your thermographer gets a proper idea or your survey will be in vain, right? So finally here, the latest addition to the building services portfolio is right here. So the increasing number of rooftop solar panels and installations. Nowadays, we have quite a lot, right? So there are many limitations and things to be checked because I have seen many derating cases where the output from the solar system, the PV installation is derated due to issues like ambient conditions of the inverters, overheating, undervoltage and overvoltage, and bad maintenance practices. So the thermal imaging also can provide a very good idea and a very overall picture about your installation as well. So moving on with mechanical applications, these are some of the rotating machinery you can find in your installations, right? Can be motors, bearings, couplings, gearboxes, many applications. Yeah, this could be really interesting for you, most of you, because this is from a leading manufacturing complex in Sri Lanka. This is a kiln. This is a tile manufacturing kiln where you have high temperature inside these walls. So you can see with the thermal camera of mine, I was able to capture hotspots like this. This is where the missing insulation is, right? So when the insulation inside the wall is missing, the thermal signatures start popping up from the outside, right? So it should be like this. But when something like this pops up, that's bad insulation. So you can also see visually, right? In the visual image certainly confirms, but again, right here, there used to be a point like this. Obviously, they repair it, right? So missing insulation, and on the bottom, we have a stack where the kiln exhaust is conveyed. You can see here in this area, the insulation is missing. From here, that is radiant insulation. So if you want to save energy, if you want to create a safer environment, right, you need to have the insulations where they're supposed to, right? This can be applied for your building services like HVAC ducting. You have chiller lines. You have cooling towers. Yep. So we're speaking of which, this is a cooling tower performance survey. This image is from the ITC from USA, where they have carried out a cooling tower performance survey. So you can see this cooling tower right here is at outdoors, right? So here, in my opinion, this is not the best time to carry out a cooling tower performance survey or an audit. So if you can see here, you can see the solar loading on this, the sunlight, right? The sunlight is not good for our surveys, right? The sunlight always masks off the important information you need to find. In this instant, you can see there is a shading right here, right? There is a solar shading right here. So in the thermal imaging, in this thermal imaging, you can see the exact pattern on the cooling tower, right? So that's the effect of the solar loading. You cannot do a survey with the sun on. I don't know why the ITC included this photograph, because it gives a very wrong idea on the matter. If I was given this job, I would stay up until the night falls, or at least the sun goes down this barrier right here, and I would let this cooling tower cool down so that I can get the real performance picture without the solar loading, right? So I can see these fins right here and how they work, how the cooling performance, what's the efficiency of the cooling, which blocks of the fins are working and which are the blocked ones, right? So there are things, there are implications. You need to have an idea of the environment you're working with. You cannot just go out there with your device and do it. If you miss something, if you don't take the solar loading into your accounting, if you don't ignore it, if you ignore it, you will end up with the bad results, and you have to mislead your client without you even knowing. That's a bad practice. Then you will never achieve the throughput the client expects from you, right? So if you're a thermographer and you're a client, now you know what to expect and what to look for, right? Oh yeah, this is another one. So you have ducts, right? You have, this is an image from ITC again. You can see this duct right here. You can see a leak from here, right? That's a missing insulation. That could be a missing insulation or a air leak from the ducting, right? To make sure, you know, this thermal imaging technology is a very comprehensive technology, but to make sure what the exact problem is, you might need some additional tools as well, right? So when you see this image, you go out there and you stand here with a ladder, and you need to check out here with an anemometer, or you need to just use your hand to make sure whether it's an air leak or an insulation breach. So just remember that thermal imaging alone sometimes will not be sufficient to get what you want from it, right? Yep, another heat exchanger performance glance. you can see these condensers after flushing and before flushing. This is again from ITC. So the pictures are self-explanatory, right? I don't have to explain it to you. So you have in your buildings, you have outdoor units, you have your chillers, you have your other heat exchangers like, say, it can be anything, right? You have your HVAC units, right? You have your coils, HVAC coils. This is where it can be applied. Yeah, this is what I was talking about in the overseas. When the winter is on the corner, you need to check your floor heating systems, right? So in the US and the other countries, this is a huge business where each and every house do the checks on their heating systems before the winter. So the central heating systems you can easily check with thermal imaging. This is from ITC as well. Yeah, your chillers, it can be refrigerant leaks, it can be either cool or hot. Either way, if you use your camera in the right manner with the right parameters, and if you use your training, you can find anything with it, no matter what. Oh yeah, leaking pipelines, classic case, right? I know building services engineers will agree. If you're trying to find a leak, a water leak after the new construction building, this is a real headache. You need to sometimes break down the concretes to get to the pipe and inspect all the way through. That's a huge cost. So this photo is from a man, Greg Stockland. Greg Stockland is a legend in the field of infrared thermography. He has been infrared a thermographer for 40 years now. He owns his own company, Infrared Cameras Inc., USA. So this is what he did. This was taken in 1992 from a helicopter. What he did was, so this facility had a huge water leak. They wanted to find where it is. So they called the Greg. So what Greg did was, he waited until the night, until the ambient temperature drops and the earth temperature drops, right? And he calls the Bowser with the hot water and he started pumping. This is the result. He gets into the chopper, he takes his imager with him and captures. There you go. Leakage points identified. But again, in 1992, this could be a costly exercise, but not today, right? We have drones with most cutting-edge cameras, and we can also use a land survey. You can just what the start point is of your line. You start pumping and you start following the hot line along the line. You will see the heat signatures. The most heated signatures will be the leak, right? So the signatures are everything. You need to have an idea what you're trying to hit and what you're trying to look at, right? So mechanical components, endless, we discussed, right? Steam traps, also you can easily identify steam traps, and with IR thermal imaging. And valves, you can see a leaking valve, you can see a blocked valve, and you can verify the correct operation. And I can talk about a little bit about devices. We saw the images, and now we know there are devices out there. I just want to give a glimpse of what's in store for you. So I'll be touching a little bit on the classification of devices. There are many types. There are fixed types. There are sensor-based types. There are portable applications. There are sensors of different types and specifications. And finally, I will tell you a little bit about device maintenance. So, device evolution, this picture speaks for itself. When Greg and others started doing thermography, the cameras are really huge. They were enormous. And today, I have one with me right now, which is pluggable to your smartphone, right? And you have smartphones in the market with an inbuilt thermal camera. So it used to be like this, right? They were huge. They were bulky. They were really hard to handle. And it's now like this. This is what we have today. Imagine having had to carry the one of the three above and the change it has made on the industry with the models we have today, right? So the reason for this size reduction is this innovation which took place in the early, in this late 90s with the innovation of the what we call the microbolometer. So before the microbolometer, the sensors, the IR sensors we had needed significant amount of cooling, which of course made them bulky, right? Some of them required liquid nitrogen gas tanks to be carried along with them, which is crazy, right? So today, what we see right here, and here, and here, and here, is the uncooled microbolometer. The microbolometer innovation completely ruled out the need for the cooling, which innovated that the devices to be really, really small, right? And so that's about the image evolution. Okay. Can you guys hear me?
Yes, we can. Yeah.
All right. Okay. All right. This is for classification of devices. Some of the devices we see today on the market and the applications. We have fixed type asset monitoring types. We have public safety, security for surveillance, and for fever detection is the latest market segment given the pandemic situation. And there are many portable types for many applications for handheld and vehicle mounted. We have other non-engineering applications. I will probably will have time to show you at the end of the presentation what the non-engineering applications are for the thermal imaging. And lastly, the gas imaging, what we call the OGI, optical gas imaging, is a very popular and very fast rising technology where you can see leaking gases using these cameras, right? The latest camera model from a reputed supplier has both options to see the anomalies such as electrical and mechanicals, and it has a separate dedicated mode to see leaking sulfur hexafluoride gases, SF6. So that's the thing now, right? Okay, details about classification. So there are many sensor types. So what we have, what we see, these point sensing instruments, the fever detection cameras we see today everywhere carries only one IR sensor. That's an uncooled microbolometer. And the focal plane array is a center matrix, right? Usually the point sensing has only one sensor in it. But the FPAs have a matrix of points. Like it starts from 80 by 60. And today we see images at the resolution up to 1024 into, I think it's 960. Yeah, 960. So this one right here is 1024 or even large. This is for your information, is the camera that the US Air Force mounts on the MQ-9 Reaper drones that they use to carry out reconnaissance and bombing missions in the Middle East, in Afghanistan and Iran. So this is one of the top cutting edge images ever built. And this is the latest. We have payloads right now. We have FPAs mounted on drones for solar PV utility installation monitoring and surveying. This one right here, of course, it's used for border patrols, frequently deployed in the US-Mexico border to track down unauthorized crossings through the border at night. These are non-engineering applications, of course. These devices, they have set of specifications. So if you are trying to buy one, make sure you study a little bit about the specifications. Make sure you know what to get, and it depends on your application. If you are trying to maintain your building service, do some predictive maintenance on your building, you should probably go to this one right here. So if you are hiring a thermographer, make sure they have at least this, right? So because this and this may not be sufficient for your survey, because the thermal detail levels in the safety regulations we have today, you need to be at a certain distance away from the electrical panels when it's energized, according to the National Fire Protection Agency 70E safety standard. So to meet that requirement, you need to be at least around at least 3 feet away from the panel. So if you are trying to hit a target from 3 feet away, the resolution 160 by 120 may not be enough to catch, right? So the temperature range is a thing. If you are trying to do a building service, you can be around 400 degrees C. If you're having a boiler in your building, check out the boiler standards and the manufacturer's maximum temperature ratings before you select one. And here, right here, non-metric, radiometric and non-radiometric. This is really interesting. This is where the price points vary really hard, right? So radiometric and non-radiometric specification has a difference of about $500 US. The radiometric means that when you have, say, we have an 80 by 60 imager, you have a total of 4,800 points on the thermal imager, right? So when you are recording a photograph through this image, you will have distinct 4,800 readings on the image when you capture. So when you come back home, you can analyze all those 4,800 points with radiometric. But if it's non-radiometric, you will only have that 1 point you measure during the survey. You cannot take it back home and analyze the other points out of the 4,800. So that's the reference. That's the difference of the radiometric and non-radiometric. So that's a big deal when it comes to post-processing of images. When you take about, say, 500 images from a survey, right? When you come back home, you can end up like with only one reading per one image, because you're looking at a camera, you're looking at a panel with so many MCBs and so many contactors, right? You need to analyze each and every one for them for anomalies. So it's important that you get a radiometric image, right? So these cameras, they have inbuilt visual camera. It starts from 0.6 and the cutting edge ones have 5 megapixels. So the sensitivity and accuracy is also a very important factor. For example, you cannot use your industrial images to measure your temperature. So I have seen this in facilities where you have a very industry image, which is very expensive, and your management tends to think that it's so expensive you can measure the people's temperature with it. Not quite. These industrial maintenance images typically carry a 2-degree plus or minus error, or from the 2% of the value being measured, which is useless when it comes to temperature screening, right? So, but these images, these point sensing devices, they have around 0.4 Celsius degrees accuracy, which is greater than accuracy than this, right? It's about the application, right? You are trying to measure temperature. Your error can be the difference between a COVID patient and who's not. So it need to be pretty accurate. So, but your focal plane array industrial camera, it's meant for a different application. You cannot switch, right? So you need to understand before you're selecting the camera. If you are trying to, however, recently after this pandemic, they have rolled out a separate firmware to these images with the EBT mode, elevated body temperature mode, so that after installing that firmware on this camera, you can carry out EBT measurements. But not for every image, of course. With these images, it was rolled out, but for these images, it was not. They were not sophisticated enough for a firmware update at this point. So you need to look at the specifications. They specifically mention that EBD mode is enabled or not. Spectral response. So in the radiative thermal physics, I told you that there are 3 subbands: short wave, medium wave, and long wave. So for long wave is the one we mostly use. For medium wave and short wave, there are many specific applications. You need to, if you are trying to measure internal temperatures of the boiler, you are going to need a short wave or a medium wave one. Remember that. So just be careful about it. Field of view, external objects. Field of view is the view that you give you, and the external optics are the lenses that you can modify the field of view. It can be narrow, it can be wide, right? And the frame rate, of course, every single imager have a 9 Hertz rate standard. And if you're trying to do some spying and reconnaissance, you would need a 60 Hertz one, because with the 9 Hertz one, you cannot monitor people's movements and whatnot. So you need to make sure that you get a frame rate 60 Hertz one if you are trying to apply for that field. So as you can see, the specifications are really, really important, right? Important when it comes to application. It is everything about the application, what you are trying to achieve. The specifications will obviously depend on it. Maintenance, all right. I have seen many poor maintenance practices. Your thermal imager comes with a carry case usually. If that's an industrial camera, there's a very high probability that it has a plastic case. Always when you're going around the site, use it as much as possible. And lenses and external optics, keep them dust-free, debris-free. Please remember that your sensor covering, the lenses, they have a special coating on them, right? This coating enables the infrared photons to get onto your thermal sensor. If you are trying to remove that coating, you are obviously wearing off your camera. Use only warm clothes. It can be wet, but no alcoholic and other solvents, right? Don't use solvents, and then solvents can affect the special coating, the non-reflective coating. Always keep it charged. Don't let it go under charge. It will be dead. And you'll be wearing off your battery. And there are some functionality checks before every survey to make sure that your equipment is in great shape and ready to go. Calibration and verification. So this is a very interesting tip when it comes to the industry. Some of the clients, they ask for calibration certificates. When it comes to cameras, some say that you have to calibrate it every year, right? That is not, of course, required because your initial factory calibration is valid for at least 5 years on the field if you don't do anything stupid. But if the client insists, you can provide a verification report. Calibration and verification are two different aspects. You can use a local vendor for verification like ITI. I have seen some reports, but ITI cannot calibrate your image. They cannot calibrate your image. Calibration is a factory adjustment. If they find that the verification is off, they will calibrate it for you. You will have to send your camera back to the manufacturers or his designated laboratory for calibration checks. So it's important that you are in sync with your OEM, your manufacturer, because they roll out certain updates. Like I said, they rolled out the EBT updates when the pandemic hits around the world. And just know what your equipment can do. Yeah, this, of course, is a really interesting topic today in Sri Lankan context and around the world as well. So remember the governing guideline for thermal imaging certification. There are many, of course. There is the ASNT, the American Society for Non-Destructive Testing Guide, which is the SNT TC1A, and the ISO has 18,465.7, right? And there are some other ASTM and other standards which I'll be touching very lightly later on. So these levels are really clear. They have their own distinguished differences when it comes to stuff like syllabuses and the curriculum of the training and the certification, minimum experience hours required, but the level is really clear in all of those. Level 1, certified professionals in thermography cannot do a survey on their own. They are only trained and certified to capture information, record them under the supervision of a level 2 person. They are not allowed to interpret the results. They cannot produce reports for you. But unfortunately, I have seen level 1 reports, which can be really dangerous sometimes, because in level 1 certification and training, they don't fully understand how to interpret an image. So for level 2, obviously you can carry out a full survey and interpret results, provide guidance to level 1. That's all they can do. But you should at least look for level 2, right? For level 3, which I am one, I can assume full responsibility for training and certification. I can train and certify level 1 on my own written practice. We call it a written practice. ASNT TC1A is the guideline written to create the written practice. But there are many training vendors and manufacturers who provide and make their own written practice to certify and train people. Yeah, these are some of the governing standards. There are many, many more. I'm just putting out there just a few of them. So the ASNT is the one I follow. I have my written practice guided by the ASNT because my certifier is ASNT certified, and their guideline is ASNT TC1. And the CP9 189 is a Canadian version, and the ISO is it's like this. Now, ASNT is for American region and some of the other regions around the world, but most of the regions around the world, including Europe and Australia, they use the ISO. They follow the ISO, but it's more or less the same, right? With the ASNT, you need to go with the NFPA 70 Bravo, 70E, and CNIDA 2019, and of course 18436 ISO 74 IRT condition monitoring, right? So if you have an imager in your facility, know that it's not a God-sent article, right? Take it out and use it. Now you have seen enough images, you know what it can do. So take it out from the box and put it out there on the field where it really belongs, right? Get your staff trained, get them certified. All right, I have been really passionate about developing potential locally. I myself support a lot of local professionals, and I have a community with me that represents many cultures and communities around the world. So I kind of know how they operate, right? How they qualify, how serious are they in the qualifications? How serious are they when it comes to the quality of the work, right? So that's why I am teaming up with NCNDT, Atomic Energy Board. They have the right-minded people there to NDT, they are the experts locally. They want to do some work, and I'm really happy to collaborate. And you need to get trained, right? The training is paramount. You need to get trained. And if you're, I would say not to worry about certification at first. If you have a imager in your facility, just do some basic playing around. That would be a really good starting point. Know how it works. Read it. Read the specifications, what they mean. Study what they mean. You can ask people like us. We are willing to help, right? We can help. We can guide, right? And you can set up a basic training program in-house. I myself watch a lot of webinars. There are pretty great deal of training materials and free stuff, free webinars out there. There are really good stuff from ITC, Infrared Training Center, USA. There are really good stuff from the My Trainers, the Snell Group, and the Infraspection. They are really generous. They have white papers. They have publications free of charge for download. And they carry out training sessions. And I must say that the quality training can be really expensive because can be really expensive. And so once you have the basic training and the hands-on culture in your house, then you need to empower the workers, right? You need to sit down with the management and discuss about this and show them what the true strength is, and stop playing around with politics and focus on the positives, focus on the performance, focus on what exactly by exactly showing them what this can achieve, show them the savings, show them the effects, right? And the framework and the base you need to create from the ground up. And the activation takes a lot of work. And you need to get out of the operations versus maintenance mentality. I have listened to speakers around the world, and what they say is, unless these two cultures get together and work on a predictive maintenance program, you can never achieve supremacy. You can never attain excellence, right? So it's a mindset shift we are talking about here with the technology activation. So it's really important that your organization do this and educate them, right? And most importantly, like I said, you need to read a lot. You need to watch webinars. You need to speak. You need to interact. You need to post. You need to stop wasting on Facebook, like I have done. I hardly visit Facebook. I visited Facebook last week to publish this my poster for this event. I don't usually go there. What my game is in the LinkedIn. In LinkedIn, I have 500 plus professionals around the world doing thermography. So all I see is thermal images in my homepage, my newsfeed. So we interact. I ask them, what is this? What is this? And I give my honest opinion. Okay, you could have done it like this. It could be better like this. So this can imply like this. So this can have this effect. So what have you done to minimize it? So that way, it's a life-changing experience. Really. You should try it. And if you are really into thermography, if you are passionate about predictive maintenance, if you want to reach excellent heights in your workplace and create a great culture, this could be your entry point, right? And take home points for the surveys. Please scan everything, right? Some I have seen that they don't scan the control panels, thinking that there cannot be any anomalies in there, but there could be. That one anomaly that makes the difference can be in a control panel. So get everything scanned if you are scanning. So the loading is a really important factor. So I said that NFPA 70 Bravo says that the load should be at least 40%, but I dictate for my surveys it should be 100%, right? Should be 100%. And make sure you know the certification levels of the thermographers and what they really mean. And when it comes to certification, I have first-hand experiences where some of the trainers they offer a certification for money. This is a really demeaning practice and should be stopped. I don't know there is no regulator for this. You just know who the high quality trainers and certifiers are. So I was offered the certification, my level 1 certification for about $1,000, which I respectfully declined because we as thermographers and engineers should always be knowledge seekers, right? The certification is just a piece of paper. You should always seek knowledge. You should always seek interaction with the fellow professionals. You should discuss. You should get their idea and what they have to say. You have to listen it. That is a way forward. The certification is just a piece of paper. Yeah, reporting can be really important because you do the survey, you do the images, you analyze them, and if the client cannot understand what you're saying, your report is useless. All that work is in vain, right? So make sure your client understands your output results, what they need to do to overcome a certain anomaly. You should be as simple as possible for them, right? And once you receive the recommended actions from the thermographer or the engineer, execute them, do it. Don't leave them unattended. It could be the worst mistake, right? So follow-up survey is highly recommended so that you know that at least your anomalies are being handled and now fine. Uh, of course, the engineering qualifications with the basic understanding of electrical engineering and mechanical engineering and the underlying principles combined with the certification, of course, can be beneficial. All right. I'll be running through some non-engineering applications quickly because it's been more than, I think, yeah, half hours. All right, this is a very nice non-engineering applications. This is called the equine thermography, where you know, the assets we know in our world are transformers, breakers, and motors and gearboxes. There's a part of the world in Europe, the horses are really expensive, right? They are also some of a form of asset. So what they do is they have created a separate stream of thermographic or equine, where you monitor the health of your horses. It can be inflammation, can be misalignments, it can be joint pains, it can be horseshoe misalignments and stresses, because these horses, they run races, they run really fast. So the difference between an injury and the victory can be a predictive survey on the horse. So this is a really interesting field of knowledge. So I have some equine thermographers on my LinkedIn profile as well. It is really interesting how they see these animals. They even have the treadmills for these animals, because we humans use treadmills to do some medical checks. They use treadmills to run the horse and do some thermography checks, so that they can warm up the body of the horse, and they would know what the anomalies are, right? These are medical applications. You can see this image is from Dr. Sandy Chambers, and this image is from Amanda Amorio. Amorio was a previous jockey for a racehorse, and he got injured. Now he's an equine thermographer. Really interesting. Medical thermography can predict some diseases, your pains, where exactly it lies, blood circulation issues, inflammation, rashes, viral diseases, fever, endless. So this is the fever monitoring. This is the camera I was talking about, right? So this is after they roll out the EBT firmware. Now this is running the EBT firmware. So this is a military NSAR search and rescue replica. This is a real photograph from a search and rescue mission in US, where the county police department found a survivor or a lost person in the jungle using an airborne drone survey using a high resolution thermal camera. And this is a mission it's a military exercise carried out by the US Navy on a coast. This image is taken out from a thermal binocular. Firefighting, of course, you can see in a firefighting environment, it's really smoky, right? You have a lot of smoke. The beauty of the thermal imaging is that you can see through smoke. You can see those thermal signatures through the smoke. So which makes the job of the thermal firefighter very easy, right? You can when you get inside the house which is burning and really smoking, you can find survivors in it. You can find the survivors' heat signature through the smoke. So this is some of the images I took from a manufacturing plant. This is a tiles manufacturing plant that we took the possibility, we checked the possibility of using thermal imaging in tile curing process. So we tried to measure the temperatures and the curing process. Yeah, that sums up. And it's time to get shooting. I'm really looking forward to the questions. I think we can now switch to our cameras, right? Right, Dylan?
Yeah, thank you, Engineer Shami, for a nice presentation. And we are moving to the second part of the presentation today, which is the Q&A session. So actually we got a flow of questions. Already we got 16 questions. And I'll take one by one and you can answer accordingly.
Okay.
For the first one, how to take thermal images of breakers which are inside explosion-proof enclosures. Next, as an example, they say at petroleum plants.
Is
How to take the thermal images of breakers which are inside explosion-proof enclosures. Engineer Shami? Engineer Shami, can you hear us?
Engineer Shami. I think he may be having a little signal and connection issue. Please bear with us for 2 minutes, please. Please bear with us for 2 minutes, please. Engineer Shami is getting a little connection issue and he's getting it rectified. So there are about 16 questions altogether, which would again give you some more information about the thermal imaging and its practical applications. So kindly bear with us without leaving. So that will help you to get more information. So those who requested the presentation material, so I think ISL will publish that in ISL web. Otherwise we will try to, we'll get his permission, Engineer Shami's permission, and share with you. So Engineer Shami is back. Engineer Shami, you can hear us? Engineer Shami, can you hear us? Engineer Shami, we can see you, but we can't hear you.
Can you hear me now?
Yes, now correct.
All right. I'm really sorry. I don't know what happened.
No,
All right.
that's-
First question, Ilan, are you there?
Yeah, I'm there. First one, how to take thermal images of breakers which are inside explosion-proof enclosures. As an example,
Yeah.
petroleum plants.
Yes. That is a really good question. I think that is one of the challenges we pose when it comes to thermal imaging. There are few remedies, of course, that won't benefit as much as we take images from a naked panel. What you can do is you can select the zone. There are zones classifications. There are some zones that you can take, keep them open for a certain period of time, but most of the zones you cannot. So in that case, my suggestion is you can do an external inspection. If the panel is, you can do an external inspection. You can check from the sides and from the up and the cable entry points to for some anomalies. If you do not find any, I'm afraid there is no option but to stop the process and take the risk out of the process, and then open the panel and instantly take images before the temperature goes down, because the temperature signature will stay for a little while. But again, if you once you open the panel, the convective currents will cool it off really quickly, that there is no other option to do it. And as a remedy, I propose to install stationary units of thermal imagers inside the camera, inside the panel, and get the signals out of it to your DCS or whatnot. Of course, this can be a costly exercise with the temperature sensors and the wiring and the interfacing SCADAs, but there is absolutely no way to track the thermal signatures of explosive-proof panel, which is completely sealed off, almost completely, I would say, sealed off from the high-risk zones, right? And for other panels, like you can try with ultrasound testing, but I seriously doubt that the ultrasound will pick up anything from the panel, because the panel is closed, sealed shut with the gaskets on. So there are no absolutely way to the ultrasound signatures to come out from the anomaly out of the panel. So what I propose is go for a continuous monitoring system with the sensor installed inside, or you can install simple RTDs inside. That's another option. If you want to track the temperature, you can, if you can see at a glance, that is also very cheap. An RTD is really, maybe a good one is less than $50. You can wire it, and you guys just check whether the interior of the panel is hot or not. Those are that is what I would do if I was given that challenge.
Thank you, Engineer Shami.
If that answers the questions.
Yeah, actually we got 20 questions in total as of now.
Wow, we're gonna be here for a while. All right.
Okay, the second one, what are the maximum temperature of different components? Example for breaker terminals, cable lugs, motor bearing, etc.
Yeah. The question is about evaluation of a hot connection, as I understand. How do you know whether it's hot, whether it's too hot or not, right? It can be hot, but we need to know whether it's too hot or not. There are certain criteria given in the NETA, National Electric Testing Association tables. You can refer those tables, and there are some criteria such as you can evaluate based on the ambient temperature. And for the component wise, of course, there is no such standard, but for cables, I would go with the insulation levels, because the manufacturers of the cable say that the maximum temperature is about 90. So I would be very worried if the temperatures reach about 90, right? And for other components like contactors and say thermal overloads, MCBs, there is no such internal component standard. Of course, there are some vendor-specific standards. You can always ask your manufacturer. For example, if you have a motor, you can always ask your manufacturer what is the permissible temperature on the surface. I have seen in some of the data sheets of the contactors, they have given some temperature indications for the maximum value. Of course, there is no such standard giving everything all in one, right? I have, from my trainers from the Infrastructure Institute, they have developed a standard by themselves for each component, but I would say that's a very good guide. But based on the ambient conditions and operational conditions, I would defer my judgment on that. Yeah.
Okay. The third one, is it possible to use thermal imaging for the refrigeration applications, such as leakages of refrigerant from chillers, leakages from ammonia from pipe connections or valves?
Yes, I actually showed an image of a chiller refrigerant leak, because the refrigerants are really cool, and once it's out, you can really easily see them. And refrigerant, if you are talking about cool rooms, etc., you can check for insulation, missing insulations, which causes a lot of electricity usage for your chillers and coolers. And for ammonia leaks, of course, if you are trying to look at ammonia leaking your pipes, you need to go for a optical gas imaging applications, because that way only you can see the ammonia, because these cameras, the OGI sensors, are calibrated and to a very narrow specific bandwidth, so that each gas is shown. For example, for ammonia, it's one tiny bandwidth. If you want to see methane, it's a whole different new ball game. It's a different ball game. So you need to specify the OGI manufacturer what you want to see. But again, if the ammonia is cooler, you can see it leaving the surface of a pipeline. There are indications you can see. The cool signatures will definitely tell you. For example, if you are talking about a cool pipeline, what I would do is I would get a hot air gun, and I would just apply the hot air throughout the line, and I would check for tiny cool spots. Yeah, that would surely show you where the leakage points are. You have to like adapt to the situation like that. You have to, of course, you guys are engineers, every one of us are. You need to apply those engineering principles and common sense into the surveys. That's why I told that this is not a simple point and shoot technology. Great question. Great question.
All right. Next one, is it possible to use IRT to track air leakages through buildings envelope?
Yes, actually, what they do is in places like US, they use the blower doors, what they call the blower doors. They seal off all the doors and the windows, and they take a blower to pressurize the house inside or the outside, so that they would know, they would see the fugitive air leaks from the walls. It can be from the walls, it can be from the windows, it can be from the doors itself, it can be from the roof, it may be from the attic. The thermal signature, it's the building inspections are a very specific and different area, which we don't use in Sri Lanka much, but it's still usable. If you have the major, you can still do it. You can still do it.
All right. The short question, next one. Can we use IRT to find water leaks in buried water pipes?
Yeah, I show you the image, the aerial image of my man Greg. Well, that's what he exactly did, right? The thing is with these low water leaks, finding surveys is that you need to wait for the perfect ambient conditions. For example, if you are trying to find a water leak on the daytime with the solar loading on the earth itself, that's useless. You can't do that. You need to wait until the earth cools down. We are talking about after 12 midnight surveys here. That is really fun, really interesting, right? You pump hot water into the lines, and you just have to follow the line. You will see the stain. You will see the signature really nicely. You will see the line, the very sharp line with the hot water on the ground itself. And when you reach the leak, you will see a big stain out of it. There is no more sharp lines. There is a big chunk of heat signatures around. That's the tip off. That's where you should be starting to dig. That is really fun. That is really fun, and that's really obvious and really common sense things you can do. It's really good. It's a really good application, and I'm sure many building service engineers will find it very useful. Good question.
Yeah. All right. Our next question has 4 parts, 4 short questions. How do you calibrate the devices? What's the frequency? How harmful IR to human, and how they verify the calibration? Okay,
All right.
The first one, how do you calibrate them?
Yeah, I will start with the number 3. How harmful is IR to humans? Because if you saw my basic slides, the IRT is about sensing. It's not about emitting from your devices. It's nothing emitting from your device. It's just the sensor is trying to capture the photons coming into the device. There's nothing emitting from the device. Of course, except for one case, if you are having these point sensing industrial images with the laser pointer, you have to be careful. Except for that, there is absolutely nothing emitting from these devices, because these lasers are class 2 lasers with prolonged eye exposure can result in an injury. Apart from that, if you switch off the laser itself, that is completely fine. There is absolutely nothing that can harm you, because they are trying to sense it, not trying to emit anything from the images. About the calibration, like I said, if you purchase a camera today, you will have the factory calibration certificate, which I should all right, the bag. You should be having the certificate saying that, okay, this was calibrated on this date, on this location, and valid for 1 year, right? And there is no fixed frequency to calibrate. This is a huge misconception and a myth in the industry. There is absolutely no need. I spoke about functionality checks, right? You can check whether your camera is functioning well. What I do is I would boil some water and check the temperature. If the boiling water gives me 100 degrees, that's fine for me. That's good enough for me. If I'm trying to measure some melting ice, if it's giving me -2 to 0 degrees, that's fine too. That's a span test right there, from 0 to 100, right? There are 2 points verified. That's good enough. And then I try to before starting every survey, I measure someone's tear duct right here, which should come to around 36 degrees if the emissivity is set to 0.98. Again, it's verified. So as long as these functionality checks are fine, you don't have to calibrate it. That's how I do it. And there is absolutely no articles or anything to prove that the manufacturers demand 1 year calibration each and every year. That's crazy. That need not to be done. That does not require. What you can do is, if your client is demanding a calibration certificate, you can get it verified locally. You can get it verified to the entire range. If your say your image is 400 degrees range, you can get it verified from a calibration service provider anywhere in Sri Lanka. But the calibration, sorry, you can get it verified. The calibration is a manufacturer's job. The calibration is about if your verification is well off. Say if you are trying to measure 400, it gives you around 420 or 25. That says that something is off. And then you send it to the manufacturer for the calibration, right? First you do the verification, and that is off only. You send it to the manufacturer to US, most of the manufacturers, they have calibration labs in Hong Kong or either in Singapore. You don't have to send it to US, but based on your model, if it is a high-end camera, you may need to send it to US. They have a fully fledged calibration laboratory. The same calibration they do to your imager when they are being manufactured. That need to be checked. And they will dissect your camera, take everything apart, they will clean it, and they will do some adjustments on the PCBs and the components to, after diagnosing what the problem is, and send it back to you. That is calibration. Remember, calibration is only needed if the verification is off. If not, there is no fixed frequency, do the calibration. I think I answered all 4 parts, right?
Yes. Yeah, that's right.
All right. All right.
Okay. Next one about specification of cameras. Do they have a limitation for maximum number of shots, or can they take unlimited shots?
There is always an internal memory to it. Like any electronic device we have in our mobile phones, they have 128 GB, 64 GB. Usually the manufacturers, they specify from the number of images. I have seen images that can store 1,000 images, 2,500, and 5,000. So it's a specification. It's a direct specification. You can take it out from the data sheet. And yeah, that's about it. And if that is radiometric imager, they will store more information on the image, and will need one single image will need a greater space than a non-radiometric imager. But again, the specification says how many images that it can store, and the specification it tells has whether it's radiometric or not. So it's self-explanatory. So when the imager says that it's radiometric and stores 5,000 images, so it's a storage for 5,000 radiometric images. It's like that.
Right. Next one. Who is authorized to carry out thermal audits?
Like I said, I need to say this, that I have seen level 1 foreign surveyors in Sri Lanka. I have heard stories about them, which is not good. Level 1 certified personnel cannot carry out the survey without the supervision of a level 2 or 3 guy. You always need to check for level 2 or above. Level 3, higher the level is better, because for level certification, they demand certain hours of field. For example, for you to get a level 1 certification by trainers, they wanted at least 120 hours on the field. That is some serious prerequisite requirements for certification. The high quality trainers and certifiers, they don't do this as a business. They do it for the quality, which is exactly why it's expensive. My trainers, they charged the Snell Group. My level 1 certification was Snell Group. That was around $2,500 US. Really expensive, but it's worth it. You will only realize when you end the course and the amount of materials you have and the amount of knowledge you have gained. The reason I'm speaking with confidence right here and answering 20 questions from the number of users right now is the confidence I gained from the training and the certification and the experience. If not for this, you will know. You just have a word with the thermographer. You just have the basic know-how. Many of you have the images with you, so you know what to ask. You already know what to ask. Ask him to show him his certification and check whether when he was certified, and if the certification is very recent, you can assess his level of experience and do a research about his certifying the training association, his training client, where he is training. So I heard this story, which is really really disturbing. There is a famous certification institute in India, where most of the thermographers, even in Sri Lanka and around the world, get certification from. And that certified thermographer is a level 3 certified thermographer. He passed away last year. This was confirmed by another associate of him. But the association, the particular company is still issuing his certification. But the real level 3 thermographer is no more with us, and the certificates are still being issued. Level 3, luckily they are not authorized to issue level 3 ones. They only issue level 2s, but the certifier is no more. So that is the type of culture that they have created outside the world, and still these things are new to Sri Lanka. So make sure you, the thermographer, you are investing a lot. The thermography services are really expensive. That is one of the major investments that the facilities manager have to make. So when you are making it, do some background research, ask around, get it certified, ask for his certification, assess his level of service, and ask him where he has been and what are ask his capabilities. Ask him to provide his sample work, right? So you need to assess him on a whole new level. And the training, the most high quality trainings are really expensive, and they demand high number of field hours. You need 120 for level 1, you need at least 240 for level 2, you need at least 400 hours on the field for level 3. That is astounding. That is really good. That is the level of quality they are demanding. Unless it doesn't matter you pay them or not, they need the prerequisites filled, because they don't certify ad hoc manner. They don't certify in the ad hoc. You need to be really careful about this. So on the baseline, level 2 and 3 can do the surveys on your facility. Level 1s cannot. And make sure you look for the certification and where the certification is being issued, and his references, etc. And what he has done, and what his contribution to research. That is also a very good point. What he has done apart from the routine surveys. Ask him whether different applications he has been involved in, which will expand the mindset of the thermographer. When he gets exposed to various environments and various problems, he starts thinking, and his mind is, it's all flowing like water when it comes to thermal anomalies. He knows what's happening. The first instance he sees, he knows what to ask, he knows the right questions to ask. Within 2 or 3 questions, 2 or 3, 4 questions, he knows what's going on. So that's what you should be looking for. It's not easy, I know, but we have to start somewhere. Sri Lanka has to start somewhere.
Yeah, the next question also related to that one. I think you have partially answered that question as well. How to get the certification in Sri Lanka? And this was asked several times, several members in the group.
Yeah, certification, of course. Right now, there are no courses in Sri Lanka. To be honest, I just got my level 3. I got my level 3 2 months ago. So I am yet to create my written practice. I am authorized, but I am not planning to issue certifications yet. For now, we will work with Atomic Energy Board, the National Center for Non-Destructive Testing, because they have the right skills, the hardware, and the people to make this happen in Sri Lanka. So that's what we are working for. We have a very able four-man team working on it. We have a great director. We have a great young minds working. We have 3 doctors and professors working with me alongside. Actually, it's a really great honor for me to contribute to that. So right now we are looking at creating curriculums, and we are trying to deploy this course very soon, really soon. This is going to be a long course. It's about, I think, 5 working days with this is a 30-hour long course, level 1, and it will be launched soon. I will make sure that I inform Mr. Narangoda and the members when this is commencing, so that you can inform your members, because as the NCNDT has rightly identified, there is a huge demand for certification. Because I was shocked the moment that I was offered the level 1 certification for $1,000 for nothing. No classes, no practicals, no high quality work, for nothing. But for that kind of certification is useless. It's just a piece of paper. You can get a job today or tomorrow, but inside you are empty. You are empty. You are not competent. So the future of the infrared thermal image is looking really bright in Sri Lanka. That I can tell you.
All right. Next one, how to select emissivity values when we scan bare conductor and an insulated conductor simultaneously.
Yeah. He must be talking about the point of termination, where you have the bare copper lines and the PVC, right? The thing is, you don't have to measure the temperature of the bare copper, which is useless. You have a high emissive surface right next to your target, which is really good enough for measurements, right? Because the bare copper you are looking at have barely an emissivity of 0.1, depending on the oxidation level. We don't know how oxidized that is. But for sure, the PVC will have an emissivity of beyond 0.9. I usually typically use the 0.9 or 0.92, which is a really good point of measurement. Sometimes you have to be tactful. Every material will not be in your favor. The materials, they exist in nature. You cannot touch them. You cannot modify them. But there are instances you can modify. If you can, if it's safe to touch, you can modify. If not safe, you have to be smart and use indirect methods of measurement, right? In that case, you can measure the temperature of the PVC, because the PVC and the copper is in a thermal equilibrium, right? They are touching each other and they are thermally settled, which can be a great reading to get an indication of how hot the copper wire is. So that should be good enough for a thermographer. So he has to get satisfied from that and evaluate the connection based on value. Because change in the emissivity is not permitted, especially if your emissivity, if you are trying to measure something beyond less than 0.7 emissivity, your ambient conditions and your reflected temperatures and humidity come into play, which is not a very neat play to do it, right? Unless you are really confident, if you have the reflected temperatures measured and the reflectivity with the diffusivity, and that is really serious level 2 business that you don't have to worry about, because you have a highly emissive PVC surface. Measure it and evaluate it. That's what I would do.
All right. How should I select a device for predictive maintenance purposes in a manufacturing plant? What are the factors to be concerned?
Yeah, like I said, if you are trying to hit a plant, you need to first select a good resolution, and you need to decide on your range. What is the maximum temperature on your facility? It can be a boiler, or it can be a panel. If you are trying to hit the power panels only, if you don't have anything else, you can be off with the lowest range device of around 400 degrees, which should cover everything you have. And for the detail level of the thermal domain, you can have a 320 by 240. And of course, it should be a radiometric imager for sure, and to post processing, and yeah, I think you can read around a little about the specifications, or you can write to me. I can help you with it to select the best camera for you. And there are plenty of white papers around the internet on how to select your thermal imager based on your application. So you need to, I think you need to do a self-study first and read around. You should be fine. You should know. You will know after days of reference. You should know. You should know what you should get it. You should get it.
Right. The next one. Is there any directory or list of class 2 and class 3 skilled persons in Sri Lanka to be contacted?
There is no such directory, but I'm trying to create one with ISL. I have an idea so that we would know where to get it, just like a chartered engineer if you want to employ. As of now, there is no such directory or a reference, which is exactly why you need to be careful. But I also have an idea to create a Ceylon Thermographers Guild, which haven't materialized right now. If we have such case, but then again we need to regulate, right? So I have an idea to create ISL, but as of the moment, I don't have it. I don't know who else. I know, of course, level 2 and level 1 personnel who know. But right now, I cannot. I mean, I don't know anyone that I can recommend or not. So there is no such directory as of now.
Right. Next one. How important of reflectivity of a surface when we capture IR image, and it might affect to final recommendation. Please discuss it.
Yes, that's a really great question, because the radiosity law, that's a thing called radiosity law. It's level 2 stuff. That says that reflectivity and the emissivity and the transmissivity is equals to 1. So transmissivity is the amount of energy traveling through your target. So most of the cases, the transmissivity is 0. So it comes down to the reflectivity plus emissivity equals 1, right? So when your emissivity gets low, your reflectivity increases, right? If your emissivity gets high, your reflectivity decreases. When you have high emissivity, you have a very effect on the reflectivity, which means you don't have to worry about the reflections, or your reflections can have a very little effect to your final reading. But like I said, if your emissivity is below 0.7 or below 0.65, your emissivity comes to play. Your reflectivity comes to play, and the ambient reflections will have a higher effect on your final reading. So there are techniques to minimize this effect, right? There are techniques to minimize reflectivity and to increase the emissivity. I would modify the surface, and there are methods to measure the reflectivity if the ambient permits. But I would not measure 0.6 below emissivity as it is. I would do some indirect adjustments, which is a really large area of discussion and takes a lot of training and practice to avoid. So that's a really large discussion to get the basic idea. My advice is not to go to low reflective, high reflectivity surfaces.
Right. We had similar questions, and I think, therefore, I skipped some questions. I think others who asked those questions who got the answers. Okay, next one. For explosion-proof panels, we can fix IR imaging infrared windows by fluke. What will be the effect?
I'm sorry, can you repeat the question, please?
For the exploration-proof panels, we can fix IR imaging infrared windows by fluke. What will be the effect?
I don't think there is a possibility to install IR windows to explosion-proof windows, but I don't think the explosion can be contained with the window installed on the panel. That is not the explosion-proof intended. They don't. It's not the intended practice, because in order to enclose an explosion, you need to have a very specialized sealing around the panel. To my knowledge, you can never have a strong sealing, and you can never have an infrared window made of. Infrared windows have several types. There is a exposed type. You have the perforated fins. You can maintain a direct line of sight, and you have these polycarbonate material windows. I don't think the polycarbonate layer comes in a explosive proof. In an infrared window can withstand an explosion. With the infrared window on it, they cannot contain the explosion within the panel. It's so strong. It's too strong for the infrared window. I don't think, but I will look in further into it. That's a great question. But I don't know whether they have developed materials to withstand that kind of point pressure to contain explosion inside the panel with the infrared window involved. That I have to check, but to my knowledge, from what I know right now, that is not possible.
Right,
that would definitely compromise the integrity of the explosion-proof panel.
Right. With that, we'll move to the last question that we got in the chat box. This is about electrical panels. What are the considerations to do thermal imaging without opening enclosures?
I'm sorry?
What are the considerations What are the considerations to do thermal imaging without opening enclosures?
Without opening enclosures, the infrared thermal imaging has the direct requirement to have the line of sight with the components inside the panel, right? Even through an infrared window or maybe a direct line of sight. You need to see the component visually. If you cannot see the component visually, you cannot see the component anomaly thermally. It's that simple. So if you cannot see the component, what you can do is you can do an external panel inspection to track a thermal signature from the exterior of the panel. If you cannot open the panel, what you can do is you can use ultrasound testing to capture any high frequency acoustics coming out of the panel that could that we could judge as an anomaly. That's all you can do with a closed panel. So I would never, when I come across a closed panel um, in the field, I don't actually do anything. If it is not safe to open, or they are not in agreement to open the panel or to remove the cover plates, so I just leave it. I just leave it, and I record that in my final report that you cannot do it, that I didn't do it, and I skip. And remember, you also need not the panel door, you also need to remove transparent covers as well, right? You need to have, if that is not an infrared window, through the transparent polycarbonate covers, you can never have infrared photons on your device. The only way to have the infrared photon devices onto your imager is to have infrared window, right? You should, otherwise it's not a successful job. It's better off you just skip the panel and maybe postpone it. We did like that in Leakages. When I was in Leakages, we did some panels, and when it's not, especially the capacitor banks, places like capacitor banks, it's not safe to open during operation. And but however, the National Fire Protection Agency safety standard 70E gives a certain barrier that you can stay out of the barrier limit and do the inspection. Actually, this standard, they don't prevent you from carrying out infrared thermal imaging surveys on open panels. You can do it, provided that you are wearing the PPEs and you are maintaining a safe distance from the target. The PPE, again, will depend on the current capacity of the panel. It can either be a simple face visor, or it can be a full arc flash suit, depending on the. Usually, we don't do arc flash suits. We encourage the client to go for infrared windows. We don't use it. And yeah, if you want to do a closed panel, that is the only way.
All right. With that, we'll conclude the Q&A session. And thank you very much, Engineer Shami, to collaborate in a better way to answer each and every questions our audience had. And with that, we'll move to the conclusion part of the webinar today. And Mr. Chairman, will you start with the conclusion?
Thank you, Engineer Dilan. So very interesting presentation and also very informative, very long presentation. So well done, Engineer Shami. So I think we took more than 2 hours from you. So thank you very much for being with us and sharing your knowledge, your experience. The other happy thing that we got a very nice audience today. A lot of questions, more than 23. That also makes some sense. Then understanding that how industry is looking for this technology. Also, I think there are many requests to get your presentation, so we'll discuss that later how to share with them. It's a well done, really informative. So with all, actually, we would like to go to the last session, which is a vote of thanks. I would like to invite Engineer Malaka Samaratna to deliver the vote of thanks and conclude the session. Thank you.
Good evening, ladies and gentlemen. This is Malaka Samaratna from Building Services Engineering Sectional Committee, and let us move towards the final note of the day. We had listened to a very interesting lecture today with the participation of more than 180 members in the audience. Being engineers, we all should be aware about trending technologies such as infrared thermal imaging in all our building services engineering related applications to give optimum output to our stakeholders. I am pretty confident that The lecture today served us in great way to enhance our knowledge. Moreover, it's been great pleasure for us to connect with Engineer Shami Mudunkotua, our research person of the day, who was well updated with IR thermal imaging technology and applications. Dear Engineer Shami Mudunkotua, thank you very much for dedicating your valuable time for the benefit of this interested audience. This event wouldn't be success if there wasn't an interactive audience like you all. Raising your valuable questions and sharing the ideas you had helped others to learn the content for the further extent. Thank you very much for everyone for the participation today. Finally, we would like to thank ISL staff for assisting us to complete the lecture successfully from the beginning to the delivery of the lecture. With that, we'll conclude the lecture today, and this is our third webinar for the session 2020-2021. We'll come up with more lectures in forthcoming months as well, and we warmly invite all of you to be part of next lectures to come. Good night, everyone.